Conservation of momentum is one of the most powerful physics tools we have. It can succeed, it can define, it can predict, it can get results when nothing else will, with an absolute minimum of setup and algebraic analysis. Momentum is not quite the same thing as inertia, although they're very closely related. Inertia, what we learned about with Newton's first law, is how hard something is to start. A scooter has low inertia, it is easy to start. A Mack truck has high inertia. Without an engine, you will not be able, under your own 2 feet and 2 arms, to be able to push that thing and get it started. It has very high inertia. They'll both stay at rest, Newton's first law says, until an outside force interferes. Momentum is how hard something is to stop, and the problem is slightly different. How hard is it to stop this truck right here, right now? It's easy. It's infinitely easy. The truck's not moving. Done. So although the truck has a lot of inertia at the moment, it doesn't have any momentum. What contributes to momentum? Well, let's figure out how something is to stop. Let's put ourselves into this picture. Pretend you are standing right in front of this truck. Your job is to stop the truck. Ready to run screaming? Ah! That's the sound of you having to stop something with a lot of momentum. Why? Why are you so terrified of the truck? Why do you plan to get out of its way? It's obvious. The truck is very heavy. It will squish you like a bug. The truck has a lot of mass. What about the scooter? If you have to stand in front of the scooter and catch the kid and stop the kid, will you be as afraid? Will you run screaming? Probably not. What do you think? Truck has high momentum, scooter has low momentum. You want to stand in front and stop it? Ready? Whoa, okay. All right, maybe that wasn't quite as easy as it sounds. Maybe that scooter may be easy to stop now, but if it's moving really, really, really fast, you are still going to get run over and you are still going to jump for the sidewalk and get out of its way. Conclusion. Classical momentum depends on mass, and it depends on velocity. If you are big and heavy, you'll be very hard to stop. If you're moving quickly, you will be very hard to stop. Put them together, I can't think of anything else that'll make us run screaming for the sidewalk. So, classical momentum, by our derivation, we didn't actually derive it, we just thought about it, P equals mv. Fundamentally, momentum is how hard something is to stop. In the example where we are physically there and we expect to stop it by touching it and holding it in our hands, we have classical momentum. However, it shouldn't take us too long to think of an important exception. What's really difficult to stop, but has no mass at all? Look up. Can you see in this room? Why? That's right, it's light. Light is really hard to stop. Someone tells you to stop a light wave, that's a tall order. You can hold up a mirror and turn it around, you can flash it in somebody else's face for a change, but stopping it is difficult. Apparently, there are other ways to calculate how hard something is to stop if it's not something you can physically touch. So when we study quantum mechanics, we will not be surprised to have a different formula for momentum entirely. In the meantime, let's stick with the classical scenario for a couple months and see what we can build in the real world that we can see and feel and touch. Word of the day is conservation. Conservation is the opposite of change. In English, when we conserve our resources, we're saying, look, there's a fixed number of resources. If we use them up, we won't have any more. Conserve energy, because once we use it up, there won't be any more. Hey, even the Middle Eastern lords of petroleum politics know this, and they're coming up with a plan B. Change is the opposite. The impulse momentum theorem that we've already studied says F delta T equals M delta V. A force over time changes your momentum. If there's an outside force, like friction or you scooting, there will be a change in momentum, right? Fair enough, we'd spend a week dropping eggs, it should make sense at this point. However, let's look at the opposite. If there is no outside force, that means there will be no change in momentum. The momentum is not going to change. It's going to stay the same. The total momentum of a system never changes. The total momentum of a system stays the same unless an outside force interferes. If you define your system well enough and there are no outside forces interfering, you know everything there is to know about what that system is and what it's going to do, because the total momentum of the system will not change. So, set up your problem. First, define your system. One ball does not a system make. In this common office toy called Newton's Cradle, the system involves all 5 of these spheres and the supposedly frictionless ropes they're on and the stand. All good. Make sure you have everything inside. Are they riding in vehicles? Are there people? Is there fuel? Is everything on board? Define the system. Once you've defined the system, check in. What is the total momentum before anything starts? Usually this is known. Better still, it's under your control. Here, take one of these nice spheres and drop it. Click. You'll have given it some velocity and off it'll go. Find the total momentum of the system. This total will not change. If no outside forces interferes, it's going to stay the same. After the big event, look at the objects in motion. See what it is they're going to do. The total momentum will still not have changed. It will be the same thing, and you can use the number in your calculations accordingly. Let's take a look. In Newton's third law, we had the problem of propulsion in space. You can't fly in space because there's no air. Well, here we go. We have our little rocket here, the professor at USC, all armed with his fire extinguisher. What's the total momentum of the system right now as he's sitting there cheering with his class? Right now, total momentum 0 is not going anywhere. What's the total momentum of the system going to be after he does anything, no matter what? Total momentum of the system is still going to be 0. 3, 2, 1, go! Look at that. The professor has released a huge amount of carbon dioxide in the negative direction. What happens to him? He gets a huge momentum in the positive direction. Total momentum of the system, 0. Rocket science? Oh yeah. Let's look at it with real rocket. Space Shuttle Atlantis is gearing up for its last flight into our solar system. They are turning on the engines, revving up the thrusters, and those thrusters are thrusting down an enormous amount of exhaust. Look at that. They are forcing the exhaust gases down. The exhaust gas forces the rocket up. Rocket and exhaust were originally at rest. Space Shuttle gives the rocket a huge downward momentum, and that means it must also acquire a huge upward momentum for a grand total of 0. This will continue until the rocket has exhausted all the fuel in these auxiliary canisters. Look at it go. 7 miles in altitude, the rocket is going to continue its first stage launch using up the fuel in those rocket canisters. What's going to happen when there's no more fuel? Approaching burnout. We're out of the upper atmosphere now. Sooner or later, we are going to run out of fuel in those canisters. What does the rocket do? What does the rocket do when it no longer needs those canisters because it's almost empty? Let's see that again. Fuel. Look at that burst in speed. The rocket jettisons the entire canister, fuel and all. A sudden loss of mass, same momentum. If our mass is less, that means our velocity has to be more. The second and the third stage of the rocket launch is when they're not only losing the gas, they're losing the canister itself. The canister falls back to Earth, where it is hopefully collected by NASA and reused. Next example, the idea of recall, aka firearms for people who take them seriously, what not to do. Okay, kid, you want your first lesson out on the firing range? Mom and Dad have taken you out how to learn to shoot straight? Oh! Apparently shooting straight is not the only problem. Even if it's your second or third lesson and you know how to shoot and you're just trying to make sure you're hitting the target. Okay, Stephanie, take it away. 3, 2, 1, cock back that hammer and fire. Oh, gotta be careful with that thing. Even if you're worried about getting hit, maybe hold it far, far away from you. Oh, that's not the solution either. Oh, that has got to hurt. Moral of the story. Any person handling weapons with any experience, including every gunner in every pirate and every Navy movie you've ever seen, where do they stand? Take a look. This is Israel Hands in Charlton Heston's classic Treasure Island. He's really going to fire that thing. And he is standing resolutely to the side of the cannon, because every experienced pirate knows that this has a total momentum of 0, and if you are shooting a cannonball with a huge forward momentum, a high mass at a high speed, right out the front going forward, the cannon itself will instantly acquire a huge and equally huge negative momentum going backwards. What if you actually want to hold your own firearm and not try holding it at arm's length? Yeah, that worked real well. Or pack it to the side? Well, take a look at the equation. You have a certain amount of momentum. That amount of momentum is not going to change. You're expecting a certain recoil velocity. That's within your control. Check it out. More mass, less velocity. Clamp the firearm against your body. Wedge it in good. Make sure, please, it's clamped against a part of the body that can take a little bit of pounding. If it can't move without moving your body, then your mass is added to its mass, and it will recoil considerably more slowly. That last example where the fellow was holding his rifle at arm's length, that is the most stupid thing he could do if he's trying to minimize the recoil that's going to hit him in the chest and knock him over while his relatives at the firing range laugh. Now let's take a look at the opposite problem, where you are so well prepared to deal with the recoil that it leads you into an error in physics. Here's Harrison Ford, the original Han Solo. Did you know that before Star Wars, Harrison Ford was not a professional actor? Yeah, he came to Hollywood and he read for a few roles, but nobody thought he was doing a good job. He didn't get hired. His career never actually went anywhere. So he stayed in Hollywood, not as an actor, but as a carpenter. Harrison Ford spent 2 years as a contractor in the Hollywood studios until some clown named George Lucas was auditioning an actress for a princess in some space opera that he was producing, and he needed some schmo to read the other lines in his script. Harrison Ford was fitting a door for Francis Ford Coppola when George Lucas stuck his head into the office and said, "Hey, is there a guy in here who could read me a couple of lines for a minute? I got an actress here for an audition, and her co-star isn't here." Ford obligingly put down his tools, came in, and read for the part of the space cowboy in George Lucas's new movie. The actress didn't do a good job and she wasn't cast, but Lucas was enchanted with this carpenter. He loved him and offered him the role of Han Solo in the original Star Wars. In addition to being a carpenter and a handyman, Harrison Ford is also a pilot. He's spent most of the last 20 years being a rescue pilot in the mountains of Northern California, at least until he discovered that desperate white single women of a certain age were getting themselves deliberately lost and hoping that he would fly and find them. Harrison Ford knows how to handle tools and he knows how to handle real firearms. Watch his wrist as he fires. See how it snaps back every time he takes a shot, exactly in the way that a real gun would recoil. This is a man who clearly knows what he's doing, with one tiny little problem. Those aren't real guns they're firing in Star Wars. Of course not. They're shooting blanks. They're not even shooting blanks. They're shooting laser light. It's not even real laser light. It's the equivalent of a flashlight that kills you. Notice they had to pen it in with the special effects. Now, I ask you, a flashlight that kills you, how much momentum does it have? That orange beam of light. Really? Oh, no mass, you say. Well, says someone else, didn't we find out that there was another formula for light that has momentum even though it doesn't have any mass? Yeah, the first determinant is Planck's constant, which is 6 times 10 to the negative 25th. That thing has no classical momentum. Therefore, blaster pistols in Star Wars and phasers in Star Trek and every science fiction weapon anywhere ever is not going to recoil. It doesn't snap your hand back like a real pistol would do because it's not losing or gaining any momentum. Blast your way out of Mos Eisley if you must, but blast it out on a trail of correct physics.